In the previous lecture, I taught you how to calculate the mean and standard deviation of a variable. Recall that the mean tells us the average of a variable, and the standard deviation of a variable gives us a specific numerical value that indicates how clustered or dispersed observations of a variable are away from the mean of that variable. Now, while the standard deviation of a variable gives us a numerical value to indicate how clustered or dispersed a variable is, frequency distributions, bar graphs, and histograms can show us visually how clustered or dispersed a variable is. A frequency distribution is a table that summarizes the distribution of a variable's values. It tells us how many observations take each value. It is mostly used for analyzing the distributions of nominal and ordinal level variables. Recall that nominal and ordinal level variables divide observations into categories, such as support, do not support a candidate, or Republican, Democrat. As an example on how to build a frequency distribution, I will use hypothetical polity 4 data. Polity 4 measures the openness of government institutions. Polity 4 classifies countries as autocratic, onocratic, or democratic. This is a hypothetical data set of 10 countries. Each country's Polity 4 classification is indicated in this column here. As you can see, there are 3 democracies in this data set, there are 5 anocracies, and there are 2 autocracies. We will use this information to build a frequency distribution. Here is the frequency distribution. In the first column, you write the term categories as the column title, then you write the categories underneath it, and add the word total at the bottom. The categories should be written in some logical order if possible. In the second column, you write the letter F as the column title. Then you write the number of observations in each category. Then you add the total number of observations at the bottom. Here is the frequency distribution example with the polity data. In the first column, you write categories as the column title, then write the categories underneath it, autocracy, anocracy, democracy, and add the word total at the bottom. The categories should be written in some sort of logical order if possible. So in this case, I wrote the categories from the least free countries, autocracies, to the most free countries, democracies. In the second column, you write the letter F as the column title. Then you write the number of observations in each category and then add the total number of observations at the bottom. As you can see, there were 2 autocracies, 5 anocracies, and 3 democracies in this data set for a total of 10 observations, which you write at the bottom here. We can also add 2 additional columns to our frequency distribution. The first is the category percentage column. It tells you the percentage of cases each category takes in the data set. It is calculated by dividing the total number of observations in the category by the total number of observations overall and multiplying that value by 100. So going back to our frequency distribution example, the category percentage for autocracy would be 2 divided by 10. 2 divided by 10. And then multiplied by 100, or 20%. The category percentage for anocracy would be 5 divided by 10. 5 divided by 10 times 100, which is 50%. And then the category percentage for democracy would be 3 divided by 10. 3 divided by 10. Then multiplied by 100, which is 30%. Here, we added a column with the category percentage as the title. Then we add 20%, 50%, and 30% to the appropriate rows. And all of these values should equal up to 100%. The last column we add to the frequency distribution is the cumulative percentage. The cumulative percentage tells us the percentage of observations at and below a given value. Note that this assumes that there is order in the data. So this is mostly for ordinal, interval, and ratio level variables. So the cumulative percentage for a category is the sum of the category percentage for that category and all the category percentages in the categories below it. So for example, the autocracy category is the first category, and there are no categories beneath it, so it only has the cumulative percentage of its own category, which is 20%. The cumulative percentage value for anocracies would be the sum of the category percentage for anocracies and autocracies. So 50% plus 20% is 70%. The cumulative percentage value for democracies would be the sum of the category percentages for democracies, anocracies, and autocracies. So 30% plus 50% plus 20% is 100%. And we add this information to the last column. We write the cumulative percentage as the column title, and then we add 20%, 70%, and 100% to the appropriate rows. Note that we leave the total row empty for the cumulative percentage column. Now I'm going to show you how to interpret a frequency distribution. The information in the category percentages column can tell you the percentage of observations within the variable that fit within each category. So for example, the autocracies category percentage was 20% here. So we can say that 20% of our observations were autocracies. You can also add the category percentages together to get the total percentage of observations in more than one category. So for example, you can add the anocracy and democracy category percentages together to see how many observations lie within the anocracy or democracy categories. So to do this, you would add 50% and 30% together to get 80%. So we can say that 80% of our cases are either anocracies or democracies. Because the category percentage column tells you the percentage of observations within the variable that fit within each category, you can use the category percentage column to find the mode of a variable. The mode is just a category with the highest category percentage in the table. So, for example, anocracy has a category percentage of 50%. Which is the highest value in the category percentage column. So anocracy is the mode for this variable. It is the most common category amongst the observations. Next, the cumulative percentage tells us the percentage of observations at and below a given value. So for example, the anocracy cumulative percentage of 70% tells us that 70% of observations in the variable are either anocracies or autocracies. Next, within the cumulative percentage column, you can also identify the median value of your data. Recall that the median is the middlemost value of a variable when that variable is ordered from the smallest to largest value, with 50% of observations above the median and 50% of observations below the median. To find the median in a frequency distribution table, all you have to do is find the cumulative percentage category that encompasses the middlemost observation or the observation at 50%. So autocracy only goes up to 20% in cumulative percentage column, so autocracy cannot be the median. Anocracy goes up to 70%, so it includes that 50% value. So anocracy is the median value of this data set. Last, the cumulative percentage column can also help you identify the top percentage of cases of a variable. So for example, you may want to identify the top 79% most free countries in the world. To do this, you start at the democracy category, since the democracy category indicates the most free countries in the world. The democracy category has a cumulative percentage of 100%. You subtract 79%, the topmost value, from 100%, and you get 21%. So 21% is going to be this bottom value. Then you find the categories within the cumulative percentage column that range from 21% to 100%. These are the observations with the countries that are the top 79% most free countries in the world. The anocracies and democracies categories hold the cumulative percentage observations between 21% and 100%. This only goes up to 20%, so it doesn't count. So 21% up is anocracies and democracies. Hence, anocracies and democracies are the most free countries in the world. In the next part of the lecture, I will show you how to make a bar graph. A bar graph is a visual representation of the data from a frequency distribution. As such, it is best used for nominal and ordinal level variables. When you construct a bar graph, you place the total number of cases or percent of cases on the y-axis and the category names on the x-axis. Then you add bars on top of the categories on the x-axis to represent how many observations fit within each category. This is a bar graph that represents the information from the Polity 4 frequency distribution example. As you can see, the percentage of cases is on the y-axis. The category names are on the x-axis. Note that I placed the variable name below the x-axis as well. 20% of the cases were autocracies, so I made the bar above autocracies go to 20%. 50% of the cases were anocracies, so I made the bar above anocracies go to 50%. And 30% of the cases were democracies, so I made the bar above democracies go to 30%. To interpret this graph, we could say 20% of the cases were autocracies, 50% were anocracies, and 30% were democracies. Now I'm going to briefly describe how histograms are constructed. A histogram is just a special kind of bar graph for interval and ratio level variables. If we made a bar graph out of an interval or ratio level variable, then we'd have to put a category on the x-axis for every single value of the variable, which would be a lot of categories. With so many categories on the x-axis, the graph wouldn't be visually appealing or informative. So instead, we create categories or bins on the x-axis that represent a range of values for the variable. And then we count to see how many observations have values that fit within the range of values for each category. Hence, the bars represent the total number of, or percentage of observations in the variable that fit within the range of values for each category. Here is an example of a histogram of common space scores from that house in the 106th Congress. Recall from the beginning of the lecture that common space scores measure Congress members' ideological leanings on a -1 to 1 scale, based on their voting behavior. As you can see on the x-axis, these bars do not represent specific values of the variable. They represent ranges of values. This makes the graph more informative and visually appealing. If there was a bar for each common space value, the graph would look very cluttered, messy, and hard to interpret. So, what did that histogram tell us about the typical member of Congress? We could say something like this. There was not one typical House member in the 106th Congress. Instead, there were two typical House members in this Congress. A liberal Democrat here and a conservative Republican about here. We could say that Republicans and Democrats have different ideological preferences based on their voting behavior. Now I'm going to show you how to describe a bar graph or histogram for ordinal, interval, and ratio level variables using the following characteristics: center and range, number of peaks or modes, and skewness. The center of a bar graph or histogram is where the median is located. You can calculate this by hand or use SPSS to do it. The simplest way to calculate the range of a bar graph or histogram is to take the value of the largest observation value and subtract the value of the smallest observation value from it. For example, in this graph, the center or median was 50, which I calculated by hand, and the range is 90, the largest value with data in it, minus 10, the smallest value with data in it, which is 80. The next characteristic of a bar graph or histogram that you should describe is the number of peaks and where they are. A peak is like a mountain peak. It creates a clear upward trend in the data with other bars following that pattern and eventually clustering around it. To find a peak, draw a general outline on the top of the bar graph or histogram. Here is a histogram of a state's vote share for Gore in the 2000 presidential election. I drew an outline on top of it. From the outline, I could see that there is one clear peak around 45. So obviously there's no 45 on the x-axis here. I just had to make a good mathematical guess that this was 45. If this is 40 and this is 50 and this is the middle between 50 and 40 is 45. So anyways, from this outline, I could see there's one peak around 45. There is an upward trend to this peak that the other bars follow, and these bars are all clustering around this peak. Here's a histogram of the Heritage Foundation's ratings of government spending. I drew an outline on top of it. From this outline, I could see that there is one clear peak around 80. There is an upward trend to this peak with the other bars that follow it. It's almost as if the bars are building a stairway up to the peak, and these bars are clustering around the peak. Here is a histogram of the UN's Gender Inequality Index for countries around the world. I drew an outline on top of it. From this outline, I can see that there are two clear peaks, one around 0.3, which I had to figure out on my own once again, because 0.3 isn't on the x-axis here, so I had to guess that it's between 0.4 and 0.2, so it's around 0.3. So there's one clear peak around 0.3, and then one around 0.7. Once again, I had to figure that out, what that value would be. So one around 0.7. So there's one around 0.3 and one around 0.7. And there are two distinctive upward trends with bars clustering around them. So there's one trend here, going up with bars clustering around it, and then a dip, clear dip, and then another upward trend with bars clustering around it. So with this graph here, the upward trend to the one peak look kind of like stairs. There are no other distinctive peaks in this graph. Whereas here, this clearly has two distinctive peaks. So to describe this, I would say that the peaks are at 0.3 and 0.7, and that the bars cluster around the two peaks. Now, when you describe the peaks in a graph, You should note how many there are and where they are. If there is one clear peak, the graph is unimodal. If there are two clear peaks, the graph is bimodal. If there are many clear peaks, the graph is multimodal. And if there is more than one peak, note if the peaks are about the same size or if some are bigger than the others. And also note, as this is a bit confusing, that calculating the modes or peaks by hand is different than identifying the modes or peaks in a graph. Here's an example of a graph that is unimodal with one mode around 50. There's one clear peak. Here's an example of a bar graph that is bimodal with one mode at 0 and the other at 100. These are two distinctive peaks, and the peaks are about the same size. Here's an example of a bar graph that is bimodal with one mode at 0 and the other at 100, and the 0 mode is the larger one. The next characteristic of a bar graph or histogram that you have to describe is skewness. If a bar graph or histogram has a negative skew, the left side of the graph extends much further than the right side of the graph. If a bar graph or histogram has a positive skew, the right side of the graph extends much further than the left side of the graph. And if there's no skew, the left and right sides of the graph extend about the same amount from the center of the graph. You could fold it in half and the shapes would be the same on both sides. Here's an example of a bar graph with a negative skew, as the left side of the graph extends much further than the right side of the graph. Here's a line I drew on top of it. As you can see, the left side is extending much further than the right side. It is extending into a negative direction, hence a negative skew. Here's an example of a bar graph with a positive skew, as the right side of the graph extends further than the left side of the graph. Here is a line I drew on top of it. As you can see, the right side is extending much further than the left side. It is extending into a positive direction, hence a positive skew. And this is an example of a bar graph with no skew, as the left and right sides of the graph extend about the same amount from the center of the graph. You could fold this distribution in half, and the left and right sides would be about the same shape. There's an additional way to measure skewness. We can calculate a numerical value that indicates how skewed a distribution is. But in this class, I am not going to have you calculate skewness by hand, as it is complicated. So you will have SPSS do it for you, and you will have to know how to interpret it in SPSS. Here I provide a simple way to interpret it in SPSS. If the value for skewness calculated in SPSS is positive, greater than about positive 0.5, the distribution has a positive skew. If the value for skewness calculated in SPSS is negative, less than about negative 0.5, then the distribution has a negative skew. If the value for skewness calculated in SPSS is close to 0, between about negative 0.5 and positive 0.5, the distribution has no skew. Here's an example of a histogram with a positive skew. And here's the measure of skewness for the variable in SPSS. The measure has a positive value, so this distribution clearly has a positive skew. And here's an example of a bar graph with a negative skew. And here's the measure of skewness for this variable in SPSS. The measure has a negative value, so this distribution clearly has a negative skew. And here's an example of a histogram with no skew. Note that there are no tails extending out either in a negative or positive direction. And here is the measure for this variable in SPSS. The measure is very close to 0, so this distribution clearly has no skew. In the next 6 slides, I'm going to give you examples of how to use center, range, modality, and skewness to describe bar graphs and histograms. In this graph, the center is 50, which I calculated by hand, but you could use SPSS to do it. Just remember it is the median value. The range is 90, the largest value, minus 10, the smallest value, which equals 80. The graph is unimodal with one mode at 50. And there is no skew as the left and right sides of the graph extend about the same from the center of the graph. And the skewness value from SPSS is 0. In this graph, the center or median is 50. The range is 100, the largest value, minus 0, the smallest value, which equals 100. The graph is bimodal, with one mode at 0 and the other mode at 100. The peaks are even. And there is no skew as the left and right sides of the graph extend about the same from the center of the graph. And the skewness value from SPSS is 0. In this graph, the center is 50, because that is the median. The range is 100, the largest value, minus 0, the smallest value, which is 100. The graph is bimodal, with one mode at 0 and the other mode at 100, and the peaks are not even. The 0 peak is the larger mode. And there is no skew as the left and right sides of the graph extend about the same amount from the center of the graph. And the skewness measure from SPSS is pretty close to 0. In this graph, the center is 50, which is the median. The range is 70, the largest value, minus negative 10, the smallest value, which equals 80. The graph is unimodal with one mode at 50. And in this graph, there is a negative skew as the left side of the graph extends much further than the right side of the graph. And the skewness value from SPSS is negative 0.982, which indicates there's a negative skew to this graph. In this graph, the center or median is 20. The range is 70, the largest value, minus 10, the smallest value, which equals 60. The graph is unimodal with one mode at 10. And in this graph, there is a positive skew as the right side of the graph extends much further than the left side of the graph. And the skewness value from SPSS is positive 0.998. Now I will use the common space scores example from the beginning of the lecture to show you how to apply what you have just learned from Lecture 3, Parts 1 and 2 to analyze a real-world variable. Recall that common space scores measure Congress members' ideological scores. They range from -1, very liberal, to 1, very conservative. As such, they are ordered and continuous, but they do not have a true zero, so common space scores are interval level. Hence, we could use the mode, median, or mean to describe this variable. However, the mode, median, and mean tell us different things about the typical value of the variable. According to the modes, the typical members of the House are either liberal, with a score of -0.374, or conservative, with a score of 0.359. According to the median, the typical member is moderately conservative, with a score of 0.137. And according to the mean, the typical member is moderate, with the value of 0.05. So which one is correct? If we look at the distribution of the common space scores, it becomes clear which one of these is the correct one. Here's the histogram of the common space scores. The center or median is 0.137. The range is 1.75. There are two peaks, so it is bimodal. One peak is around -0.374. One peak is around 0.359. The 0.359 peak is larger, which means there are more typical conservatives in this Congress than typical liberals. There is no skew because if we folded this distribution in half, it would appear about the same on both sides. Note that the skewness value is 0.309, so it's relatively close to 0. Based on this information and what the distribution looks like, it is safe to assume that there is no major skew in this graph. Based on this information, it seems like the mean of 0.05 is not representative of the typical ideological position of Congress members, as there are very few Congress members with common space scores close to 0.05. We can make a similar observation about the median, as few Congress members have a common space score near 0.137. But we can say that the modes are representative of Congress members' common space scores because there are a lot of Congress members with common space scores near negative 0.374 and 0.359. So based on this information, we can conclude the common space scores demonstrate that there are two typical types of Congress members. One type is liberal, the other is conservative. There are more typical conservatives than typical liberals, since the 0.359 peak is larger. There are very few moderates in Congress.